section, what we're going to be learning is how to run two different tests. We're going to learn how to run a 1 proportion test and a 2 proportion test. And this is the part of the class where things get a little bit more interesting. This is because we can start to ask questions that are maybe more interesting to us or relevant to us. So for example, let's say we saw the claim that more than 10% of the population believes in ghosts. We could actually collect data asking people whether or not they believed in ghosts, and we could test this claim. Or we could look at the claim less than 2% of the population has been to jail, and we could sample the population and test this claim as well. Examples of 2 proportion tests compare groups of things. So in the 1 proportion test, we're given proportions or percentages to test. Whereas in 2 proportion tests, we're actually comparing 2 groups of things. So again, if we're looking at whether or not men believe in ghosts more than women, or women believe in ghosts more than men, we could sample 100 women and ask them whether or not they believe in ghosts, and compare that then to 100 men and asking them whether or not they believe in ghosts. And then compare those 2 proportions to see if they're statistically different or not. So learning how to run those 2 tests is the goal of this section. But in order to do that, we have to learn a little bit about what's called a sampling distribution. Sampling distribution is the distribution you would get if you were to repeatedly sample the population. So for example, let's say you randomly flipped a coin 25 times, counting the number of heads that you get. So you can calculate the proportion of heads. That would be 1 sample. But let's say you did that repeatedly. So again, we're repeatedly sampling that population of coin flips. What your repeated samples might start to look like is something like this, where sometimes you get more than half heads, and sometimes you get less than half heads. Sometimes you get all heads, which would be up here. Sometimes you get no heads, which is down here. But those instances are obviously very rare. Most of the time you get something that's pretty close to 50% heads. So the look of this distribution holds anytime we're looking at a proportion in general. So again, if we're looking at the proportion of people that have gone to jail, or the proportion of people that believe in ghosts, this is true for any histogram of the sample of proportions. It's going to be centered around the true proportion. So if the true proportion of people who believes in ghosts is 10%, then our samples are going to be centered around 10%. Sometimes we'll get more than 10%, sometimes we'll get less than 10%, but it'll be centered around that true proportion. As far as the shape of the histogram goes, it's unimodal, it's symmetric, and it's again centered around that true proportion, which means that we can apply the normal model in figuring out and answering some of our questions. In order to apply the normal model, all we need is a mean and a standard deviation. So we said that our sampling distribution is centered around that true proportion. So this is saying the mean of our samples, p hat denoting a sample proportion, is equal to the true population proportion. So I want to make a distinction here between p hat and regular p. P hat is the sampling proportion, the sampled proportion, where regular p is just that true proportion. We can use that true proportion in order to calculate our standard deviation of those samples, and that's just going to be p times q divided by n. Q here is just the proportion of failures, so it's just going to be 1 minus p. That's what the q represents. So for example, again, dealing with coin flips, our coin flips should be centered around 50% heads, but sometimes we're going to do a little bit better than 50% heads, and so the average is just showing that centered, where the standard deviation is capturing the fact that sometimes we get more than 50% and sometimes we get less than 50%, and that standard deviation captures the amount of variation we would see in those proportions or those percentages. So here's a picture of what we just discussed. Again, the sampling distribution is just a theoretical distribution where our proportion that we're interested in is centered around the true proportion, and our samples are going to vary some. So here we get variation in our samples. Within one standard deviation, we should see 68% of samples. Within 2 standard deviations, we see 95% of samples, and then within 3 standard deviations, we see 99.7% of samples. So let's do a problem so you can see how this might be useful for answering questions. When the field of probability and statistics was first developed, it was mostly developed for testing fairness of coins. Gambling was really popular in the 16th and 17th century, and so that's the reason why probability became really popular. So here you have a coin and you flip it, and 68% of the time it comes up heads. So we want to test whether or not this coin is fair. But testing whether or not the coin is fair really depends upon how many times you flip it. So let's say you flipped it 25 times and that gave you a proportion of heads of 68%. So we can compare that 68% to what would be a true fair coin, which would be 50%. So the true proportion should be 50%, and this difference might just be caused by sampling variation, that some samples are going to be a little bit higher than 50% and some samples going to be a little bit less than 50%. So maybe this difference is just due to sampling variation. We can test to see if that's different by looking at the z-score of this 68%. The first thing I want to do is calculate the mean and the standard deviation using that proportion. So we know that the true population proportion should be 50%, and so this is the mean. The standard deviation then is just the square root of p times q. So p is the probability of success. Q is the probability of failure. A failure here is going to be tails, and so that's 50-50. And we're going to divide then by the number of times we flipped the coin, so that's the sample size. And that's going to give us a standard deviation of 0.1. We can use that mean and standard deviation then to calculate our z-score. So we put our observation first, the mean is subtracted off, and then we divide that difference by the standard deviation, and that's what I've done here. When I calculate this out, I get a z-score of 1.8. So this number represents how unusual getting 68% heads is. So getting 68% heads is 1.8 standard deviations above average. That's not that unusual because remember we said that 95% of samples should fall within 2 standard deviations. This falls within 2 standard deviations, and so it's not that unusual. But let's try this problem again, but let's say this time we flip the coin 64 times. So now our sampling distribution is going to change because we're sampling more often. So the mean is going to be the same. It's going to be still centered around 0.5, but our standard deviation is going to be much tighter because we're sampling more. We're dividing by a larger number, and so our standard deviation actually gets a lot smaller. And so seeing a 68% heads is going to be more unusual because you would expect less variation from that true center, so that true 50%. When we calculate the z-score then for the 68% observation, we get a z-score of 2.88. So this says that getting 68% heads means that this is highly unusual. This observation is highly unusual because only 5% of our samples should fall outside of 2 standard deviations. So there's only a 5% chance that this coin is actually fair. That's a really low chance, and most likely the coin is not fair, and that's why it's coming up heads. So having a larger sample size means that you've tested it more, And so you can have a stronger confidence that what you're rejecting or what you're finding is unusual. A couple of points I want to quickly make before we move on to doing problems is first I want to notate the difference between the two different standard deviations. I've used the word standard deviation a lot, but there are different standard deviations that we've been looking at. First, what we learned in the first exam was how to calculate the standard deviation of a sample. So this is when you go out and you collect data and you generate the variance of that data, and that's how we get the standard deviation of a sample. It's notated as S. Here, in this next section, we're dealing with the standard deviation of a sampling distribution. This is completely theoretical. It presumes that we know what the true proportion is. So for a coin flip, we do know what the true proportion is. It should be 50-50. But we don't always know what this true proportion is, and we're going to deal with that unknowing later. But for now, I just want to make the distinction that these are two different standard deviations. So when I say standard deviation, or if you see it in a problem, make sure that you know which standard deviation the problem is referring to, a sampling standard deviation or a sample standard deviation. The main reason why we can use the normal model to approximate our probabilities is because of what's called the central limit theorem. I'm not going to go over the central limit theorem, but just know that it allows us to use the normal model and that larger samples get us closer to the truth. The larger samples also give us more confidence and more accuracy in ours. So more data is always better with statistics. We did make some assumptions, however, in using the normal model, and these assumptions are here. First, we assumed that we have randomized the data, so we've got a representative sample of the population when we sampled. That means it has to be unbiased and representative of the population. These are important criteria because if they're violated, your proportions aren't going to be anything meaningful. Most of the arguments in the popular media surrounding statistics generally have to do with violations of this condition. Either their sample is not representative of the population or they've biased the sample in some way. The next condition is that of independence. Remember that independence means that one trial doesn't affect the results of another trial. So with a coin flip, this is pretty obvious that if you flip the coin once, it doesn't affect the results of the next coin flip. So you can flip 10 heads in a row, and the 11th coin flip is still going to be 50-50 heads. However, if we're dealing with population proportions where we're surveying people in the population, for example, my example of surveying people and asking them whether or not they believe in ghosts, people's responses may affect one another. So if I only sampled people, let's say via Facebook, I'm only sampling my friends. And so that is going to lead to a biased estimate because those relationships are dependent. So there's two ways to test for independence. One is that you have to be sampling no larger than 10% of the population. So that means you want a large sample size, but you still only want to be sampling a small proportion of the population. The second one is called the success-failure condition, and that just means you have a large enough sample size to generate meaningful statistics. So let me show you quickly how we could test these conditions given a sample. So let's say, based on past experience, I found that 60% of my students believe in ghosts. Now, I've had about 1,000 students in the past, and so that's my population that I'm referring to, is those 1,000 students that I've taught. I randomly sample 10 students from the fall of 2016, and I can test then the 10% condition and the success-failure condition to see whether or not either of those are violated. And we can see that the 10% condition is not violated because 10% of 1,000 is just 100 students. and 100 students is greater than 10 students, so my sample is smaller than 10% of the population. So that's not violated. What is violated is the success-failure condition. So the success-failure condition says that the number of successes has to be greater than 10, and the number of failures also has to be greater than 10. So the expected number of successes is 6. So I've sampled 10. 60% is my chance of finding someone who does believe in ghosts, and so I would expect 6 people who believe in ghosts. For failures, I would expect 4 people who do not believe in ghosts. And so both of these are violated because they're both less than 10. So that's what we're referring to. And we're referring to a sampling distribution for proportions. It's a theoretical distribution, and the theory is that we could repeatedly sample a proportion and get a distribution or a histogram for that proportion. That histogram would be centered around the true proportion, and our standard deviation would capture the amount of variation between samples. Now, in reality, we're not going to repeatedly sample. We're only going to sample once. But we're going to get to that when we start doing testing. For now, we're just going to work on problems that deal with what the histogram would look like if we were to repeatedly sample. And so the idea with these problems is that we are repeatedly sampling, or it's as if we are repeatedly sampling.